Hello. Oh, what are you doing? Okay. It's raining here right now, so if one of my dogs gets scared and barks, and probably I don't know if it's raining when you watch it, but it's raining when we're recording right now. It's raining for me, but not for Miss Young.
It is
So
not raining here in Little Rock.
yeah, but in in Malvern it is right now. So whatever, and this is like in June 26th. Hey, wow. Okay. Anyway,
I do have my function shirt on.
yeah, I just got a polo on. It's from my alma mater, but
I actually feel like maybe this is a pretty good shirt for this lesson because we're going to talk about so many different functions
yeah,
today.
you're going to be like wiggling your arms if I know you at all, because that's what she does. So we're going to talk about inverse functions today before we jump into the rest of chapter 5. Chapter 5 is going to be
People talking in my background.
what's that?
Can you hear the people talking in my background?
I can't hear anything because all I'm hearing is the rain and you.
Okay.
So yeah, it's raining pretty good here. So I'm not, I'm sure that at some point my dog is probably going to get really mad. So you'll just have to hear her barking or something. So anyway, what we want to talk about today are inverses. And I want to think, I always like when I get a new math term, I kind of like to think about why they named it that way and what the word might actually mean. So when I think of the word inverse, I think of like turning something around or doing it backwards. Okay. Um, what do you think of?
I mean, yeah, but that's just because my math background that I just
Yeah.
think about like undoing something. The actual word in verse, I don't know enough to know like what the verse part of that means. You talk and I'm going to look it up.
Okay. You're going to Google it, but I really like, I don't know, the nearest, yeah, if I try to decipher this word, like right here, this word, the near one of the, it sounds a little bit like reverse to me. Okay. And, I'm used to from driving. There's the big R in your shifter, and that takes you backwards. Okay. So being inverse is mathematically the equivalent of that. And Miss Google, do you have an answer for us?
Nope, I didn't get it on my first pass.
She doesn't know how to use the Googles. All
You're
right.
ridiculous.
You are. They probably don't even know. They probably think I actually don't realize it's called Googling something. I'm making fun of George Bush when I say the Googles. Okay. That's another story. But
You're
not,
making
I don't. Oh, wait. I got to get my iPad. Who's going to teach this lesson if I don't have my iPad? You, because you probably can do it faster with your mouse than I can with my stupid iPad. All right. So anyway, it's the opposite. And the nearest, actually, it's something that we do all the time. If you've ever done Control Z, you've done an inverse. Oh my gosh, we're not paying you to Google and update your Facebook, all right? Or you're on the like Snapchats and stuff.
Really?
Okay.
I quit.
All right. Well, you should, because all it is going backwards.
Well, I was trying to do it in the word parts.
Okay.
I
All
should have
right.
done it in advance. I'm sorry, guys.
All right. So when you think of this, it's like Control Z. I'd like to go the opposite direction. I did something. I don't want to do it no more. I want to undo it.
Yeah.
Okay. So what's the opposite or the inverse of a number plus 5?
Well, if I want to take away what was done was +5. So to take that away, I would do -5. If I Control Z a +5, I -5.
Okay. I don't think we want to like stick with Control Z forever, but it works.
Well, I'm there now.
Yeah, we're there. We did it. We said it. Okay. And that's, I mean, we're making a bigger deal out of this, but I want you to stop and think about this, because every thing in math, and I think I've said this before to you guys, every time you learn something in math, it's not going to be too long until you learn its partner, the opposite.
Yeah,
okay?
what will undo it.
Which will undo it. Math is all about being able to make a prediction of something and then be able to go back and forth. Okay. So that's, I mean, really, we made it harder than it had to be. So you might just want to forward through all that.
You're welcome, guys. We just wasted 3 minutes of your life.
Okay. So the question is, in math, are we able to undo a mathematical operation. Sometimes we can, sometimes we can't. We did a lot of examples of functions, and this is one that I kind of used to be near and dear to my heart. I don't eat fast food as much anymore. Miss Young probably does. She probably goes to McDonald's all the time. But at that dollar menu or the whatever, if I go to McDonald's and order a $1 hamburger off the dollar menu, they're going to charge me $1. But if I went to McDonald's and said, hey, I got something off the dollar menu, that doesn't tell you I bought a hamburger, because there might be French fries on there, or there might be a drink on there, or whatever. Okay. I don't know what's on the dollar menu, if there even is a dollar menu anymore. Okay.
There's still a dollar menu.
Yeah. It's just,
I'm not Googling that. I'm not doing it.
Yeah. Well, yeah. Please don't Google the McDonald's dollar menu. You'll be here for half an hour. Right. So what we mean by that mathematically is we've been talking about the domain and the range. The function takes you from the x value to the y value. And our purpose with an inverse function is to get from that y value back home to the x. Okay? So if I were to ask you to do this function here, g of 4 in the absolute value, that would be the absolute value of 4 plus 1, which gives me a big old 5. Right? And then if I were to ask you to do the absolute value of negative 6, it would be negative 6 plus 1. I'm not doing this. And that also equals to 5. Okay? So that's fine. That's what we've done all along. But if I wanted to if I asked you this question, what x value gives y equals to 5? Right. And that was the first question I asked you. You couldn't answer that question uniquely. Right. You could answer.
Think about it being like a mapping situation, right? Where you've got, 4 mapping to 5, and you've got negative 6 mapping to 5. Right? And then, but what if we ask you to go backwards? What if we ask you to map 5 back to an x value? You would have 2 paths to choose. Should we talk about the road less traveled right now?
If you feel the need, I don't know which way to go. Which path to choose? Okay? Right. If I'm going from the left side to the right side, I have unique individual paths. And the whole deal about functions is that they have to be uniquely defined. Yeah. So if I'm trying to go back from 5 back to the original, this is the x, and this is the y. We're trying to go from the y back to the x. I don't know which one to go to. I'm like Dorothy. I can go back to Arkansas or I can go back to Kansas. I don't know which one.
Arkansas or Kansas?
Wow.
Okay. So what we want is unique mapping. And when we have unique mapping of every x maps to 1 and only 1 y, and every y maps to only 1 and only one x, then we call that a one-to-one function. And those one-to-one functions are what we're most interested in when we talk about inverse. And we're going to talk a lot about that. This one is not one-to-one because 5 maps to 2, right? So this wouldn't be one-to-one.
And we want that predictability. That's what that one-to-one gives us. Okay. All right. So let's move on. So the notation for a function inverse is this f to the negative 1. And that's not really a negative 1. I shouldn't even say it. This is just f. We read that as f inverse of x. Okay? And what we're looking for, we know we have an equation that takes us from x to y. Right? We can go from x to y. But we want another function that takes us from y back to x so that we can go uniquely in a loop. And if we have that, then we have an inverse function. We have a very predictable function in both directions. And that's good because I want to, like, if I know that if I work 20 hours, I'm going to make this amount of money, right? I want to know how many, if I need this much money, many hours do I have to work? That's what I want to do, is I want to be able to go back and forth. okay? So f of 6 is equal to -1. This is f, okay? And when we go backwards, like this, that's f inverse, okay? And I think this is actually really terribly unfortunate notation because a lot of people think that -1 has to do with putting it on the bottom of a fraction. Don't do that, okay? Please don't do that, okay? So
You can do that later when that's on a variable
yeah.
and not on a function name.
So this would equal to 6. We're just turning it around. That's all that the inverse does. It flip-flops x and y, okay? So what if, Miss Young, I don't understand B.
Me neither. I'm confused.
Yeah, 5 is the domain. So something, wait a second. The domain of f inverse. All right, let's think about this. We're going to have like, this is at, and this is, I have 5 here, right?
Why do you have 5 over there, Mr. Bobby, and not 5? If it's in the domain, why isn't it on the left bubble?
Well, the inverse takes me backwards, right?
Right.
So there was something over here. I don't know what it was.
Some x.
Something that got me to go here.
Yep.
And that was f, right?
Yep. And then f inverse.
F inverse. I thought you were doing it. Okay, sorry.
Yeah. Takes you back.
Okay, so let's follow this thing right here. Okay, I'm going to do a different color. So I know that I got to start inside the parentheses, right?
Yep.
Order of operations. So I'm going to start on f inverse of 5, and I'm going to go over to this thing that I don't even know what it is. That's what that is. But then
so now we have f of something.
I don't know what that is. But what am I going to do? I know that that something
has to map to
5.
5.
Wow. So wait a second. I think we kind of talked ourselves through it. So what is the function when I take a function? All right. Have you ever hit Control Z too many times? Like one too many times? I have. What do I do if I hit Control Z one too many times?
You go back to where you started.
I go back, yeah. But if I hit it, like if I wanted to undo the last thing I did, but I did undo twice, then I'd have to hit Control Y. So if I do Control Z and Control Y.
We're just like, what you're doing? What? These people don't know the shortcuts.
Control Y is redo, right? So like if I undo and then hit redo, I get back exactly where I started. That's what we're saying. All right. I think we were both saying it. We're just saying it differently. So, okay. Let's get into the real crux of the matter. Finding the inverse of a function. If you have an equation, you already have an equation. We've been just talking theoretically and talking about the notation so that you get a feel for what we're going to be doing today. Ooh, did you hear that thunder?
I do hear that thunder.
Hear that thunder. All right. It's like lightning and thunder. Okay, so here's what we're going to do. The steps for finding an inverse. I'm hoping I have enough room here. We're going to replace the function name with y. And then we're going
to be clear here, guys, step 1 is just to make your life easier. There's actually only one step in this entire series of steps that does the inverse part, okay? So the first step where we replace f of x with y, that's like, let's not write f of x a bunch of times. Let's just write y. So y equals 5x minus 2.
So I'm going to write y equals 5x minus 2. Okay? Do you want me to number them? All right, so that's step 1. And then step 2, I'm going to do the flipperino. And this is the key point. That's what it does. When we said we're turning it around and changing the direction. We're literally changing the variables because we're changing the direction. So it'll be 5y minus 2. Now I'm done. That's actually the inverse of that's the inverse equation. But people don't like that. Why don't we like that?
Let me pause you for just a second, Mr. Bobby, and I'm going to say a couple pitfalls that I've seen in the past where people are working on this. See, the 5 stayed in place. The coefficient did not move with the variable. Coefficient never moves with a variable when you're writing when you're writing an inverse. If it had an exponent, the exponent would not move with the variable. It would stay in place. So it's important that only thing you change are the position of X and the position of Y.
That's why I should have been delivering this lesson from your house, and you should have been delivering this lesson from my house. That would have been funny.
Actually, this would have been a good lesson to.
Yeah, it would have been a good lesson for us to switch houses.
Yeah.
So, but that's a lot of work and a lot of travel for an illustration that I think is kind of overblown. So anyway, but now I need to solve for Y. So what am I have to do? I'm going to have to add 2 and then divide by 5. Mm-hmm. Can I? So it would. I'm going to like save myself a little bit of work here. X plus 2 is equal to 5Y. And what's going to happen when I divide by 5, I'm going to have X plus 2 all over 5. So that's going to get me the third step over here. And I'm going to rewrite the Y on the left side because it makes me happy to have the Y on the left side. But it doesn't matter. X plus 2 all over 5.
And I'm going to pause him one more time and just talk for a second about just intuitive math, because if I have a -2, then I would expect in my inverse to have a +2, because that's that operation that will undo -2. And I have a times 5. And so to undo times 5, I would divide by 5. And so if I'm talking about this X right here, I would multiply by 5 and then subtract 2. But if I'm undoing that and everything's reversing, then I reverse the undo operations. So I would take my X, I would add 2, and then I would divide by 5.
You do the same processes backwards, right?
Right.
So reverse processes, reverse backwards.
Yeah.
That makes sense. Whatever. I should just let you talk. And then just to make it align, oh, that was a funky F, we would replace Y with F of X. So really, the rest of it's just being pretty, okay?
Yeah.
Except for that, my handwriting.
Giving it a name.
Giving it a name. This is like Bob inverse, if I wanted to, okay?
A girl, no, a boy named Sue? Is that what that song is?
My last name, what's my last name? It's just, okay.
Bobby Corey. Corey, yeah. Bobby.
You know my brother's name?
No.
I haven't ever told you this. My brother's name is Dylan. Think about it.
Bobby Dylan.
Yeah, keep going.
Dylan Bobby.
Dylan, and his name is Dylan Bobby, yes. Think about it a little more.
Wait, am I supposed to be getting something from this? Like Bob Dylan?
Yeah, that's my brother. That should tell you about my parents. Why? Oh, you know what? Nothing's working because I still have my pen. My brother's name is Bob Dylan. Well, Bobby Dylan, but
his name is Dylan Bobby.
Yeah, but I mean, he was named after Bob Dylan. So.
Was he really named after Bob Dylan, or are you just that's what you?
My parents were hippies. What can I say?
Well, what hippie were you named after?
I wasn't. I was. All right.
You were named after a race car driver.
Yeah, that's true. All right. All right. So we have graphed 5x minus 2 and x plus 2, the quantity, over 5. The blue graph is the function, and the red graph is its inverse. And we've just picked a couple key points. We wanted you to see, we picked 2 points on the graph. We put 2 nice points so that we could see them. And they are, what do you notice about these 2 graphs, or what are you thinking?
So I hope right now you're comparing 1, 3, and 3, 1. 1, 3 on the blue graph, 3, 1 on its red graph. And you're noticing that X and Y just literally switched positions, just like you saw us do in the equation. Same with -2, 0, and 0, -2. They're literally just switching position. Input becomes output, and output becomes input.
And they're perfectly flip-flopped.
Yeah.
There's something else that maybe you might notice, but if you might have to turn your head a little bit to look at it.
So we always want to think about, like, is there some symmetry here in the graph that we think might hold true always, right? Is there a place on the graph where we could fold it and it would sit right on top of itself? And do we think that's going to hold true for all inverse graphs? So in this case, there's a line. I think we've actually mentioned this line before by name. It's called the identity line, y equals x. And let's not make it blue. That's a little
I'm working on it. Oh, she's so demanding. What color would you like it to be?
Make it, no, yellow. We never do yellow.
There's a reason. Ah! Okay.
So you can see if you folded the graph along the line y is equal to x. Oh heavens, what's happening?
I was trying to make it darker for you, but it didn't work.
It was plenty dark on my screen.
Okay.
So if we folded along that yellow line, that the red and blue graph would sit on top of itself. So we say that if we reflected an inverse over that, or a function over that line, if we reflected it over, that we would get the graph of the inverse. Maybe think about it like this. If I were to trace the blue line with wet ink and then fold along the yellow line, its imprint would be that red line.
Okay. So that's a way to tell, that's a way to graph the inverse, or at least to get a feel for the sense of the graph of the inverse if you don't solve it. The ones we'll see in this lesson mostly will be able to be solved inverted, or to solve and find the inverse, but some cases you'll have equations that you can't, and then you would have to do that little ink blot thing that Miss Young was talking about. So, all right, we good to go back?
Yeah, let's go back.
All right. So we have looked at the function and its inverse and saw that they are reflections. Okay, so let's look at a couple problems here. So this is kind of what I was talking about before with the absolute value graph. Remember, we had two inputs and we got the same output, and you're like, well, then I asked you what number would map to that, and you were like, what? That was stupid. All right, so now I'm going to go the other way around. Can you find an x value for this function that gives me the output of 27? So what am I asking in that first question? If you don't understand what I'm saying.
Is there, and no, we're starting with this function x cubed. So is there an x that I could plug into x cubed that would result in 27?
So what I'm trying to do is like do this. Can we solve that equation? Or I hope so. Maybe I can. Maybe I can. Maybe I can't. I don't know. What is it? Do you know?
So let's see. 1 times 1 times 1 is 1.
Okay.
2 times 2 is 8. 3 times 3 times 3 is 27.
Okay. So x equals. Is there another though? Are there any others? What about -3?
Well, -3 times -3 is +9. And +9 times -3 is -27.
Oh, I was close. Does that count?
Doesn't count.
It counts in horseshoes. Can it count here?
I feel like it wouldn't. I feel like that would be like throwing over your shoulder.
Oh, okay. Yeah, I'd be going backwards and hitting somebody behind me.
Right, because it's negative, right?
I hit Dad at the grill. Okay. So what about doing the same thing? Is there a number that would give me -8? Because you did it. You got 8 a little while ago, but that's not. You told me that's not good enough. So
yeah.
2 times 2 times 2 is 8. So what about -2 times -2? Yeah, that's it. It's -2. Okay. And there ain't no other option that I can come up with. Okay. So all I don't want to do is I want to compare. We saw that graph before. It was x plus 1 or minus whatever it was. I guess I had it. Did I mess this up? Let me see. Did I mess this up in my notes? I'm going the wrong way. I did. It was +1. That's supposed to be. I thought I messed this up. That's supposed to be a plus. Right there. Sorry. Fix this in your notes, folks. I'll even try to do it in black.
Ew, you're gonna write in a boring color?
I can use a different color besides pink occasionally. Okay. So what I want to do is I want to compare the graph of x cubed to that one we did before that we said didn't have an inverse. Okay. I guess I really didn't need to, because I'm right here about to correct this, or clear this all out anyway. So let's go back to the calculator. All right. And look at the next page here. Here is the graph of the absolute value of x plus 1. This is that one we did that when we plugged in 4 and -6, we got the same thing. So actually, let me go here and trace on, or put on these points here, because we plugged in 4, right? And then we plugged in -6.
Yeah.
Okay. And we saw those both got connected to 5. All right. So this is y equals the absolute value of x plus 1. Now I'm going to do what we did before with the inverse.
Let's just do it right here on the screen.
I'm going to do it right here on the screen this time. Okay.
Here, I got you. Y equals the absolute. Oh, you didn't want to do it this way algebraically?
You can do that. You're right. But what I'm going to do is I'm going to graph the inverse for you. Okay. And the n-spire, if you delete, let me get out of here.
Mr. Bobby, what do I do at this point when I get to x equals the absolute value of y plus 1?
If you,
how do I solve?
Okay, well, we would have to plug, we could solve it, we break it in equations or whatever. I'm going to put in that equation. X equals absolute value y minus 1. You don't actually have to solve for y to graph in the n-spire. So I actually graphed, this is the, remember I told you a few minutes ago, that the x value, we solve it for y so it looks nice. We can, so that's what we're used to. But I actually can graph something that's not solved for y.
Right.
Okay. So I have the black graph there, x plus, the absolute value of x plus 1 is the function. And this blue graph is the graph of its inverse. Mm-hmm. Okay, now what's wrong with that blue graph? If I take these points that I had up here before and put them on this graph, I'm going to have a point at 4, 5. I'm going to probably regret this. I wonder if I can do this.
I was just wondering what will happen.
Yeah, I can put a point there. I wonder if it'll let me go the other way. What's going to happen when I go past 0? It did it.
Nice.
Wait, what was it?
I had doubts for a second.
Yeah. I went 5, 4, don't I? No, that's not what I want. Yeah, it is. Okay. So I've got this point. No, I wanted -6, didn't I?
Yeah. Well,
Never mind. I wanted 5.
You want 5, 4 is what you want.
Yeah. Except you wanted.
But you're trying to show this.
Never mind. Yeah, never mind. This is the right point. I want 5, 4, which would be right there, right?
Yes.
Okay, sorry. I'll get it right one of these days.
He's trying to stack 2 points on top of each other for a very specific reason, guys. So that's what's happening right now is sometimes math teachers have to think through the point they're trying to make. Point. No.
I get it, as you said, point.
And while he's doing that, I'll tell you that the only way that I could solve x equals the absolute value of y plus 1 is to break it into 2 pieces. And this is the point that he's trying to make right now is that, you know, if we take the inverse of an absolute value and we turn it on its side, we violated a really important test. What test do we violate, Mr. Bobby?
The vertical line test. This point is vertical to this point. So that blue graph is the inverse, but it's not an inverse function.
Right.
Okay, that's my whole point. And if I go back and I throw that line y equals x on there, it's going to.
Yeah, because guys, this is an inverse. It absolutely is an inverse. It's just, there's not one single function that will map back to a specific location. We actually need 2 different functions to map back to the correct location.
Sorry, that didn't work out. It took me a minute to think through that, so thank you for bearing with me. But these 2 points are vertical, whereas these 2 would have been horizontal. So if the function if the reflection fails the vertical line test, what can we tell about the original function? What
That
is
it
the
would have failed a horizontal line
yeah,
test.
these 2 points being horizontal cause the reflection points to be vertical. So
Yep.
instead of me going through all of this silliness, why don't I just look at the original graph and see if it blows up on a horizontal line test? And that's actually a thing.
Yeah. So now let's go to 1.3 and look at, because don't we have x cubed?
Yeah, we have x cubed now. We're going to clear out so if I do that same thing now, and I'm not going to worry about the points necessarily, but if I were to type x equal y to the third, when I switch those x and y's that she's writing there, I'm going to get the graph of the reflection. Now, yes, the process told you to solve it, but I'm just trying to get you to understand this idea of the vertical line test and the horizontal line test, and to see the reflection of that over the y equals x. So if I were to...
The pink graph, it's passing that horizontal line test. And you can see that it's inverse. That black graph is now passing the vertical line test. And I can very easily take the cube root of each side of this and come up with an algebraic function. The cube root of x is equal to y, or f inverse. And you can then see, okay, well, for sure, x cubes inverse is a function. I can find it algebraically, and then on the graph, it passes the vertical line test.
So if I can get a picture of the graph and say, oh, it's not going to pass the horizontal line test, I don't have to do any of this in the first place. So it's a real quick way to test to see, or based on what we know about those parent functions, there are certain ones like cube root that we're going to be good on, but ones that we're not going to be good on, like absolute value, because it failed the horizontal line test, or if you think of another one like the parabola that we spent a gazillion hours on, or any even degree polynomial, it's not going to pass, and even degree polynomials are not going to pass the horizontal line test. So,
you know, I actually think this is worth a conversation really quick. Go ahead. We add a page and graph y equals x squared.
Sure.
Going off script again, guys. Going off script.
We're just doing our thing here.
So imagine now, because we don't have to use that relation tool that he's using, if I take y equals x squared and try to imagine what's that inverse function going to look like. Well, you've got the point 0, 0. You've got the point 1, 1. Both of those, when I flip them, are the same. You've got the point 2, 4. It's going to become what point, Mr. Bobby?
It's going to become 4, 2.
Going to become 4, 2. And you can begin seeing this side of that inverse. Well, what does that look like in your parent functions? Try to imagine or try to remember what that looks like. Well, you might not have.
I'm sorry.
That looks like a square root. So you end up with x equals y squared over here. And you take the square root of both sides, you get square root of x. But if you don't use a very specific thing, if you forget something that's often forgotten, you're only going to get this. Is this the entire graph? Well, no, we didn't take into account this left side, right? We've got -1, or excuse me, -1, +1 becoming +1, -1. We've got -2, +4 becoming, 4, -2. And now you can see the negative square root of x coming in, giving us that inverse graph of at y equals x squared. But it took two functions. It took y equals x and y equals, it took y equals square root of x and y equals negative square root of x to get an inverse. And you can see it fails that horizontal line test. And then if you try to look at that graph, it would fail the vertical line test.
Okay.
It's sad. It's a sad graph.
Because it's not a function. It doesn't get to play the function. It doesn't get to play function games.
I see. Okay, I went on long enough. Let's go back to our...
All right, let's go back to the actual lesson. And all right, so we've examined these two graphs and compared them. And basically what I'm going to talk about now is what we just already been talking about, is that horizontal line test. The horizontal line test is if I can imagine or draw a horizontal line through a graph, that I can't if I can draw a horizontal line through it, it's not going to be invertible. So this guy, no inverse.
Well, no inverse function.
Yeah. No inverse fun. Okay. So it's not, yes, I can reflect it. I can get its equation, but I won't have a predictable way to return back home. So Dorothy goes to Oz and has to stay there because she can't find her way back. Okay. This one would be this one would have an inverse. I can't find any place where I would fail the horizontal line test. This one is okay. And this one is a sad face. You don't get to play function games. Okay? And Ms. Young did say that if it does this, if every x maps to a unique y and every y maps back to a unique x, we say it's one-to-one because there's a unique pathway both directions. Okay? So we use that term before we even defined it, but that's not uncommon.
Sorry.
That's okay.
Jumping the gun.
Yeah, jumping the gun, but Ms. Young and I do our own thing, so. All right. So moving on, let's do a couple more. Maybe we can inspect some graphs or whatever. So I'm going to go off script here a little bit too, and Ms. Young can do all the algebra or whatever. But I see a cube and a plus or minus 4. So I think I'm going to need to have a plus 4 in my answer somewhere. And since I have a cube, I'm probably going to need a cube root somewhere in my answer. Okay, now that's not my answer, but it's me thinking like as a intelligent human before I start to mess with this, okay? So she's written it with the y just for the sake of convenience, and she's now doing that step 2, that inverse step. So we'll get x plus 4, and there's what I was thinking a moment ago. And then to solve for y, we got a cube root. So hey, it's not like terrible, okay? So keep going. Or we can just look at it here, okay? And I didn't like these colors, but Miss Young thought they were beautiful, so I left them there. I mean, like, that looks like mustard and pickles. So well, I guess it could be like a hamburger or something. I don't know, but it's kind of gross looking. So we got the green graph is the x cubed minus 4, which
it could be like a hamburger patty, lettuce, and mustard.
Yeah, something like that, or pickles or whatever. But it's still pretty disgusting colors. Anyway, I also thinking. I remember I told you I thought there'd be a plus 4 and a cube root somewhere in my answer, and I see that, and I'm feeling okay. But I also stop and think, what do I know about the graph of x cubed? X cubed is that guy, right? That guy, John Travolta, the weirdo. Okay, she's got a shirt. Pull the shirt up. Yeah, there he is. There's that guy. But he's that graph that slid down for. Well, that transformation isn't going to make it less likely or more likely to pass the horizontal line test. Okay, and then the cube root is the John Travolta. He's falling and he can't get up. Yeah, John Travolta. The cube root is like the old John Travolta where he's falling and he can't get up.
Okay. Wow. He needs one of those like buttons.
Yeah, he needs one of those life alert buttons, okay? And that's what this yellow graph is, okay? So this passes the vertical line. We can still see that. And one thing to note, that brown dotted line was not part of the graph in any way. It was just there for your visual, okay? So anything else you want to say about this? Thank you for doing all the writing while I did all the gabbing.
You're welcome.
And continuing to do it when I took away your white space. You're a superstar. Just a little bit more about the inverses and diagonal reflections. You can restrict a domain, like we talked about the failure of the quadratic to be to have an inverse function. But if I limit the domain, then I can get an inverse, and the domains and ranges are fully reversed, flipped. That second one is not actually that's a reflection over the x-axis. One of the things that people always mess up, a lot of people seem to mess up, is they think that they get mixed up with the vertical and the diagonal reflection. Okay, so our range would be 3 to infinity,
So you would expect your domain to be that because you're switching x and y, but your domain here is actually negative infinity to infinity. It's another clue that something has gone awry.
Or a marble, or a wheat, or a sourdough. That's bad. But the reflection, would look, I mean, if I wanted to do the reflection, which I think is what Miss Young was trying to do, is, let's see, that would be at 4, 1, so that, or 4, -1, and 4, 1, so 1, 4, so it'd be 4, 1 right here. The graph would look, the reflection, the diagonal reflection would look something like that if I could draw.
Guys, the easiest way, if we give you a graph and we say graph the inverse, is just to pick some points, switch x and y, plot them, and go.
Yep. That one at the bottom, though, is I wanted to caution you, don't confuse this with the vertical reflection over the x-axis. That's no bueno. Okay. All right, now we have inverses. If I take that away, okay. But that graph that we have recreated is not a function. Okay. All right. I think we've got that well established right now. So.
I think they know. I think they just are super comfortable with that.
All right. So good. Now that you understand the concept, now we get to do great green gobs like we go in the algebra.
What?
Let's do a hard one.
Okay.
I want to put, because I don't even know. I mean, like, I got pluses of 3s and minuses of 2s and divisions and
so many x's.
Yeah, because the algebra has been easy in this section, and I don't want it to be that easy. So
at least I don't have to do step 1.
Yeah, at least I took away step 1. So all right, well, let me see here. I'm gonna give I'm afraid I'm gonna need a lot of room in this one, so I'm gonna give myself. I gave myself a lot of room, so it must be a hard problem. So it's gonna be x equals y plus 3 over y minus 2.
Yeah.
Okay. And I'm gonna, y can't be,
doesn't equal 2.
Yeah, I know. I'm gonna say y is not equal to 2, and that's gonna be.
You know why? Because of division by 0.
Oh gosh, I think they know that that's not a good thing anymore.
Sorry, Leo. I didn't mean to wake you up. Go back to sleep.
Okay. Now I gotta.
Rain here now.
What?
I said it's pouring down rain here now.
Good. Now it's stopped here. Well, maybe.
My husband just went out for a run.
Good. Then he won't stink as bad. So I got to get the y's all alone on one side. But I get y all alone. So I need help here. Maybe
so what about we multiply both sides by y minus 2?
Okay. So I'm going to do y minus 2. Yeah, I don't like fractions, and we did say that would be a good strategy, right?
Yeah. But this is the process we've used every time for this, guys, but you could actually put x over 1 and cross multiply if that's, your preference on how to solve this. I don't know what your algebra teachers have been teaching you. I mean, they're amazing, but I don't know what they've been teaching you.
I'm going to get xy minus 2x equals to y plus 3. It looks worse. And I'm not going to copy the y minus 2 each time. I'm going to assume that and deal with that at the end, okay?
So we need to get all the y's on one side of the equation, Mr. Bobby. Let's get all the y's together.
So I'm going to bring the y that's on the right side over to the left. X, y minus 2x minus y equal to 3.
Yeah, but I don't want that term that doesn't have y in it. That's confusing me. So let's move it.
Oh, so you want to bring this guy over?
Yes.
Okay. So, and I'm not going to write every step because I actually know what I'm doing, but I'm not going to let you know that. Okay. Feeling a little better, but I still got x on the left side.
Now, how in the heck? I don't want to have 2 y's, Mr. Bobby. How can I go? What's a process where I could go from 2 y's to 1 if I can't add or subtract?
Well, they're like terms with y, so there's an x and a minus 1. So could I say x minus 1 y's?
You can.
Weird. I could, but I have a GCF too.
You do have a GCF. I think maybe the students might be a little more comfortable with us
Some GCF
Factoring out
action.
the y. Yeah. But guys, what he did is like, it makes sense if you think about it. I'm actually going to stop and talk because I think we got some pretty brilliant students that maybe have never thought about it this way before. If we have xy minus 1y, imagine it were 3y minus 1y. If it were 3y minus 1y, and maybe we'll do that first.
Yeah.
Let's make it 3y. Then it would be 2y. You would do this in your head. You would do 3 minus 1, and you would get 2, and that would be 2y, right?
Writing isn't showing up.
Do what?
Your writing is not showing up on my screen.
Oh, can you move us? Because I'm writing in the top right.
You're writing on the very top left corner.
Yeah, sorry.
Oh, sorry. You were writing under my head. I see it now. My apologies to your brilliance.
Yeah, so 3 minus 1 as finding the coefficient. So what he was saying is if you have xy minus 1y, you could just say, okay, well, that would be x minus 1, whatever that is. We don't know.
I don't know, but I know it's got a y after it.
Yeah.
And it's still the same, ends up being the same thing as factoring the GCF out, but that's pretty sophisticated thinking. Maybe
it is. But we got some pretty brilliant kids here, so.
Yeah, I think they can get that. So.
Yeah.
But you know what? Either way, I have the y almost by itself. I've got y times something, and if I got y times something and I just want y, I just got to divide by that something, right?
Yeah.
So I'm going to divide by that something, except I need to do my pen to do that. So I would have x minus y, 1, I'm sorry, x minus 1. Now this is kind of where Miss Young's philosophy on equations here kind of doesn't always work out real nice. And maybe there's a way I could rewrite this equation. I was expecting like a -3 and a +2 in there somewhere.
Yeah.
And I didn't quite get that. It's
confusing when there's fractions, yeah?
But, you know, that's okay. Now, I'm not even going to try to graph the original function. I know I'd have an asymptote at, I do know I would have, in the original, had a vertical asymptote at x equals 2. And so I would expect a horizontal asymptote at y equals 2. And I do have that in this case. If you're from the last section, these are first degree polynomials, and with a 2 and a 1. So I'd have y equals 2 as a horizontal asymptote for this function, but that's more than
which we pre-found right here, guys. We actually pre-found that at the very beginning when we rewrote.
Yep. And it still bears itself out in the equation. So I should have had that along all the way, or you're bringing it down.
And we might mention here that like this function has a restriction at x equals 1.
Yes. Okay, so I think that takes care of all of that. And let me clear that out, all that beautiful writing, and move into your assignment. And that completes section 5.1. So happy day, folks.
Hi, you guys.
Wave at the end of a Zoom. I never like at the end of a meeting wave goodbye to you before, but I always have to wave goodbye in a Zoom. I don't get it.
I don't know. I'm waved to him, but I always
wave. Bye, guys.
If I could hug you, I would hug you.